Hola amigos, now let's complete the spacecraft dynamics with orbital plane change and hyperbolic excess velocities. These two are the last two topics of this subject. And just before that we will see that for rocket propulsion, in rocket propulsion you will see that we can compute delta V, total delta V budget that we has computed earlier. Delta V total can be expressed in terms of rocket propulsion parameters as well. That is in terms of ISP, specific impulse, MI, initial mass of the rocket including fuel, payload, structure, everything, and the final mass, that is MF, when the whole propellant gets consumed. Okay, and this MR is the mass ratio of final to initial mass. So inverse of mass ratio will be MI upon MF. And lastly we have U equivalent, that is the equivalent velocity of the rocket. And delta V total or delta V budget in total is given by ISP G ln MI by MF. This is natural log of initial mass to final mass, which is equal to ISP G ln, G is acceleration due to gravity, natural log inverse of mass ratio, and ISP into G is equal to the U equivalent, that is the equivalent velocity of the rocket or the exhaust coming out of the rocket. Okay, this is equal to delta V total is equal to U equivalent natural log of inverse of mass ratio. So let's complete it. In spacecraft dynamics earlier we have studied two orbital maneuvering while transferring Hoffman transfer and one tangent burn, and lastly we have these two maneuvers, that is orbital plane change and hyperbolic excess velocity. So first we will see orbit plane change. In this, let's say a satellite is revolving in this orbit which is inclined at an angle I from this orbit, horizontal orbit. Okay, and the horizontal orbit and this inclined orbit are of same size. Okay, now the satellite is to be brought from this inclined orbit to this orbit by keeping a change in velocity of delta V. Since the size and shape of the orbit in inclined orbit and the horizontal orbit is same, the velocity in both the orbits will be same. Okay, and from this we can say Vi, that is velocity at this point, intersecting point Vi, and this velocity in the horizontal plane which is intersecting at the same point is Vf, and they both are equal in magnitude, and only the change in velocity occurs because of the change in angle from inclination I to 0, I equals to 0, which can be seen from here. That is, from parallelogram law we can say delta V equals to under root of Vi square plus Vf square minus 2 Vi Vf cos I. Okay, and delta V, and this comes out to be, since Vi equals to Vf, then delta V is equal to Vi sin I by 2, sorry, here sin I by 2 will be here because inclination angle is I. Okay, just a second, please bear with me, and here as well. Okay, so now we are done. That delta V will be delta V equals Vi sin I by 2 equals Vf sin I by 2, because Vi equals Vf. So from this, cos theta in terms of sin theta by 2 we have just substituted, which can be computed, and delta V in terms of Vi and Vf is like this. Lastly we have hyperbolic excess velocity, and in this we see that when the satellite is launched from Earth, that is CG represent the Earth, and when it is launched from the Earth at a point at a radius RB0, it is the burnout point. This point D is known as the burnout point at a distance RB0 from the center. And when it reaches the burnout point, it is given this excess velocity V infinity, not only to escape from the gravitational influence of the Earth but also to keep moving in the space. And V infinity is that excess velocity which makes it keep it moving in the space, in the free space. And V infinity and VB naught are at the same point D, that is burnout point, which can be seen like this. At point D, V infinity is like this and VB naught is like this. VB naught is the burnout velocity, V infinity is the excess velocity, and VE over here you can see is the escape velocity. It is the minimum escape velocity which is required to overcome the gravitational influence of the Earth, and it follows the hyperbolic V escape is the parabolic trajectory, and V infinity follows the hyperbolic excess velocity, because the velocity which is greater than the escape velocity, minimum escape velocity, is excess velocity. Okay, and excess velocity follows hyperbolic trajectory, which is why we have hyperbolic excess velocity V infinity, which can be computed like V infinity square equals VB naught square minus V escape square. From this diagram we can see. And if we talk about only the parabolic trajectory of the spacecraft in the space, then we will have VB naught at point D equals 2gm by RB naught, because distance is RB naught, and VB naught will then be equal to the V escape velocity in parabolic trajectory. We have known this thing from our earlier lectures as well, and since VB naught is equal to under root 2gm by RB naught, and this will be equal to under root 2gm by RB naught, and here V infinity according to this expression will tends to 0, that is there will be no excess velocity to travel, keep on moving in free space. Therefore it only follows a parabolic trajectory up to a point till its potential energy and kinetic energy gets balanced, and the gravitational force of the Earth at a point gets diminished, or say it becomes 0, exactly 0. Okay, and here we can see it will attain a velocity of VB naught equals to V escape, which is equal to under root 2gm by RB naught. And with this we have completed spacecraft dynamics, orbital mechanics and gravity as well. Thank you.